Thank you for the opportunity to speak here. What I'm presenting today is joint work with Felix, Otto, and Markus Tempelmayr, who's also in the audience. It's actually quite good that Ilya stopped his course right after the positive renormalization, because basically I will use a similar framework. So I hope not to confuse you a lot with the notation that I will be using, which might be more related to the older notation in high-res works. But anyway, the main feature of what I'm presenting is that I will do essentially the same as done in regularity structures, though changing the index set. So I will come from a different motivation, change the index set, so no use in trees. And in the end, I want to end up with similar algebraic structures, which in the end allow me to build a regularity structure. So what we do is the following. We're focusing in the following class of quasilinear equations just with additive noise. So just one nonlinearity, which is A. And we actually think of treating all nonlinearities at once. So in a certain sense, we see the solution U as a function of the nonlinearity itself. But very soon we realize that that's not enough to provide a solution, because even for a fixed nonlinearity, you have actually kind of a manifold of solutions, which you can think of it being parameterized locally by polynomials. So in case of Ilya's course, there were basically this space of initial conditions. It's basically anything that you can choose to pick a solution from your manifold. Okay, and once we have this a P space, or I would call the polynomials P, we introduce coordinates in this space, which are basically given by the Taylor coefficients of both A and P. And that naturally motivates introducing this multi-index notation over variables z, k, z, n, so either for products of the sets or for partial derivatives with respect to these variables. And as I said, we want to consider U as a function of the nonlinearity A and the polynomial P, so it makes sense to take derivatives with respect to the z, k, z, n variables. And if we do that and apply Leibniz rule to this equation, we just get the following strange expression, which actually is quite nice, because for a given beta, it turned the nonlinear problem into a linear problem. So the beta in the left-hand side does not appear on the right-hand side. It only depends on betas, which somehow have shorter length. And we can actually write this whole family, which is an infinite family of linear PDEs, more compactly as a PDE in this formal power series algebra. And okay, I will not get into details, but actually, assuming some sort of uniqueness of this equation, we can actually see that not all betas will give a non-vanishing contribution to this pi. So in particular, we will only be seeing contributions which take the form of En, so what we will call purely polynomial multi-indices, and these essentially correspond to the polynomial sector in high-res language, and the others which satisfy this condition with the bracket being larger or equal than 0. So then we see this pi, this formal power series pi, as actually an element of a proper subspace of the formal power series space, and the notation T star is it's taken because it's actually the algebraic dual of what in high-res theory it's called the model space. And in by some scaling arguments, we can also introduce a homogeneity, which we can actually associate to a multi-index. So the main part of my talk is going to be how to build the structure group, which is like the most interesting thing that we did so far in the algebraic side of this construction. And yep, sure. Yes. Yep. Depends on the applications, but I mean, we are, yeah. Actually, so what we will impose in the end is, so essentially, I mean, when we construct the central model, what we would use just to have uniqueness is to have, to impose the vanishing condition around the base point. So here you should see pi x instead of just the pi. And then we also impose a growth condition when we're looking at the whole space. So kind of by a Liouville argument, we can have uniqueness in that sense. Yes. Well, I mean, actually, yes, yeah, somehow, yeah. Okay, so in order to perform this recentering operation, which is encoded in positive renormalization or the structure group, we will consider the following two actions in this AP space. So one is the action of a shift in space-time, which is seen through the polynomial P. And the other one is the action by tilt of the polynomials itself, which means that you take the polynomial and you just let another polynomial act on the first polynomial by addition. The way we treat constants here, as you can see, is a bit weird. I think I won't have the time to get into this why we do that, but anyway, feel free to ask later. And also, yeah, so we, the shift and tilt, we lift to endomorphisms of these algebra functions on AP space, which are parameterized by these coordinates that we defined before. And in a certain sense, so already you could see that from Ilya's course, when we want to recenter the model, we will use information from the model itself. So it's natural to extend this tilt not only to constant polynomials, but to polynomials which actually depend on AP themselves. So that gives the expression below. And it's easy to check that that provides a monoid, but in general, there's no clear group structure. So that's why we will need this machinery of Hopf algebras to help us. So the outline of the construction is as follows. So that's not a commutative diagram at all. It's just the steps that we will follow in the construction. We'll first consider the infinitesimal generators of these two actions, which will give us a Lie algebra, which actually incorporates some kind of pre-Lie algebra, which I will explain in detail later. And from the Lie algebra, we will go to the universal enveloping algebra, and then build a duality pairing between the universal enveloping algebra and this T plus, which is actually related to the T plus that Ilya introduced before. And then we will just finish the construction by seeing that T plus is a Hopf algebra. That's the more important step. And then concluding by general theory, so taking the group of characters of that Hopf algebra, seen through the lens of a co-module structure, which takes us to a model space. So the most important things here, and the ones that I will discuss the most, are how to build this pre-Lie algebra, and then how to do this pairing. So for the Lie algebra, we will consider the infinitesimal generators, as I said, which have these explicit expressions, so d0, dn, and we extend them to variable tilts by just adding a multiplication to the left. So these should be seen as endomorphisms of the form of power series space. And on the other hand, the generator of the shift in one of the space-time directions is given by that other expression. So a nice feature of these objects is that if we restrict the gammas to our populated case, they actually preserve this proper subspace that I defined before, this T star. And on the other hand, we can show that all these elements are actually derivations in the power series space, so they carry a natural pre-Lie product, which is just encoded like that, so kind of a covariant derivative. However, the pre-Lie product between two of these shift generators cannot be expressed as a linear combination of the previous things. So in the end, what the structure that we get in the end is not a pre-Lie algebra because it's not closed under this pre-Lie product. Some connections with the existing literature. So the pre-Lie product that I defined before with the Z gamma dn resembles the curvy arrow in the paper by Ivan Punet, A.J. Chandra, Ilya, and Martin Heira on renormalizing SPDEs and regularity structures. Whereas the generator of the shift resembles the increasing decorations operation at the level of trees. So now with these objects, we actually can define a Lie algebra, where the Lie bracket is just generated by the pre-Lie product, and where we don't have a pre-Lie product, it's actually very easy to see that this shift generator should commute. So in the end, it doesn't create any problem. And thanks to this extra restriction of the homogeneity of the multi-index gamma being larger than this n, we get the following two properties. So on the one hand, strict triangularity, which is the Lie algebra version of the triangularity postulate that Ilya talked about in his lecture. And on the other hand, we can also define a quantity which provides a gradation which is strictly positive in the Lie algebra. So now we have a Lie algebra. We go to our universal enveloping algebra, which is naturally a Hopf algebra. And thanks to our additional structure of the gradedness, we can show that it's connected and graded. So this universal enveloping algebra carries the concatenation product, which is, so just concatenating two elements, and a co-product which is naturally defined just by how it acts on what we call primitive elements, so the elements in the Lie algebra. And we actually want to think of U of L as rather than, so instead of thinking of U of L as a space of endomorphisms, we actually want to dissociate this identification. So now we think of U of L as being some abstract space together with a representation row which then identifies each of these elements in the universal enveloping algebra with the corresponding endomorphism. And this row is actually defined canonically on how it acts on the elements of the Lie algebra and then extended to U of L by the universality property. Now the next question, we want to do this duality pairing. And for this, we need to choose a basis in our universal enveloping algebra. So what we do is we take some advantage of the fact that we have a Prelim structure which allows us to actually decompose Z gamma dn into the multiplication part and the derivation part. So in the end, we can generate elements which look like this in the universal enveloping algebra. And now since the multiplication operations and the derivation operations commute among themselves, this new element djm is actually order independent. So we don't get a Poincaré-Birkhoff-Witt basis, which would require an ordering in a set of generators of the Lie algebra. We actually do this transformation, which actually, so we take this basis, which is actually order independent. This actually, when we started doing this thing, we weren't aware of this work by Gunn and Udom, where they actually build an isomorphism between the universal enveloping algebra and the symmetric algebra. This is kind of going in the same direction, although we do that explicitly, and that's convenient because in the end we use this expression to have like very explicit formula for the elements of our structural group. And here I have to give credit to Yvan Prunet and Dominique Manchon, who I think were the first using this Gunn-Udom procedure in the context of regularity structures in a very recent paper. So another feature of this basis is that it's normalized with this j factorial m factorial, so that helps giving a canonical co-product structure, so it's just given by that. You would recognize that by like the Hopf algebra or the co-algebra of differential operators, for instance, with the right normalization. Definitely, yeah, sorry, yeah. Yes, yeah. Yes. Mm-hmm. So no, I mean it's definitely no coincidence. So chance relation is then the like the product formula on the dual side. So here I will build then a polynomial algebra from this co-product. So it's definitely related. Yeah, I will actually provide that example at the very end of the talk. So yeah, perhaps we can discuss it later. So it will be so not quite. I mean, it's the Prelim product is kind of the Grossman-Lassus. So when we go to the ODE setting later, it will be clearly Grossman-Lassus and Konkheimer. It's actually the same kind of operation, but with a different. I mean, but not the free Prelim algebra with that operation somehow. It's the same kind of Prelim product where you. Yeah, I mean this. The choice of the basis is coming from the Prelim product, which is kind of grafting to certain polynomial decorations, in a sense. Yes. Yeah, we actually don't know how this would work with the shuffle. I mean, that's something that we are not thinking about because the setting that we are using is closer to branched rough paths rather than geometric. So I don't have a clear picture of what this would mean in the geometric context. So yeah, I don't have a clear answer for that. Okay, so then with this choice of bases, as Rosa pointed out, this is a co-commutative co-product, which then will give rise to a commutative product on somehow the dual side. So we build a duality pairing between these elements djm and some elements in this polynomial algebra over the variables indexed by the space-time directions together with these pairs of gamma n. And you can think of these polynomial algebras being essentially the same as the one that Ilya was defining, where you have this x to the m, and then you have a product of things. Here I'm not including noises, so in this case it's yeah, not quite needed in what I'm writing, but it's essentially the same type of construction. So we have this commutative polynomial product, and then it's just a matter of how we can transpose the concatenation product and turn it into a co-product. And also this representation row being transposed and getting a co-module structure that is non-trivial, that requires some technical properties which are related to finiteness properties of the structure coefficients of the Hopf algebra U of L. But in the end we can do it, and it turns out that T plus is a Hopf algebra and that T delta is a left co-module over T plus as required in regularity structures. So a little bit like in Frédéric's course, forgetting completely about the antipode here, but it doesn't really matter because the existence of the antipode is just justified by the gradedness in the end. So it's just not very hard to obtain it. And then the rest of the story is well known. So then now we have a Hopf algebra, so the rest is automatic. We just use the Hopf algebra with the co-module to get the group of characters and then seen through the lens of the co-module, so that's a known story. Essentially, we follow the same steps as in higher. Okay, so this might have been fast, although I hope not too fast. Now what I want to do is actually treat the example of an RDE, which is simpler because it has like smaller index set, and I think it helps clarifying what we're actually doing. So we consider, as I said, this rough differential equation type, where, now we parameterize the solution really just by the nonlinearity A, because here the solution space is actually parameterized only by constants, so by initial values. So we can actually forget about the polynomials. We turned this nonlinear ODE into a family of linear ODEs, which is just given by that expression here. You would have to look at each of the beta components of this equation. So here are some computations which you can see. So the E0 multi-index would correspond to solving the equation with right-hand side psi, and then all of them will come just somehow inductively. And as you can see, most of the times in the right-hand side, we will see linear combinations of different things. So it's actually getting larger and larger, as you can see here in the last example. In the same way as I said before, for the quasilinear case, you can see that not all components of this pi will be populated, so some of them will vanish. And the condition not to vanish is actually encoded in this nice identity, which is just telling you that you can build a tree from this multi-index in a certain sense. So as I will explain later, this beta k corresponds to a node with, let's say, k different children. So this difference here is just the difference between edges and nodes. And the fact that it's equal to -1 is just telling you that you can build a tree out of this multi-index. And as I said, we can forget about polynomials. So then the Lie algebra actually reduces to the span of these elements. So just set gamma and D0, which was the generator of this shift in the solution space, which is linearly isomorphic to the model space itself. So in the connecting to the tree-based language, so in branch rough paths, in Gubinelli's work, we could actually see something like this. So you can interpret, if you have a tree which is built from adjoining to the root family of trees, tau 1 to tau k, we can write this differential equation, which is like the differential form, like the differential version of an iterated integral. And we actually have a lemma which tells us that we can pass from our description with multi-indices to the description in trees just by this operation here. So our pi beta will be just a linear combination of these iterated integrals, or these branched integrals better, where we have this set T beta, which is the set of trees with beta k nodes of a given fertility. So we're just grouping trees in terms of their fertility configuration, as we sometimes like to say. And this motivates defining kind of a dictionary between the multi-index description and the tree-based description, which is just encoded here. And just so we can compute some examples, this would correspond to some simple multi-indices. And as you can see, multi-indices encode really linear combinations of different trees. So as Kurush was anticipating before, we can see this structure that we have, we can put it in relation to Gross-Malason and Konkheimer in the following way. So we consider a basis which is dual to trees with a Prelim product given by grafting, but now the normalization is just the number of cuts where you can recover the things that you grafted in the beginning. That's the Prelim algebra structure that appears in this work by Ivan, Ilya, Peter, and Rosa. And actually, we can show that the transpose of a dictionary is a Prelim morphism. So the Prelim algebras are compatible. But however, our Prelim algebra is not free, and that's quite important. So it's actually smaller than the Gross-Malason Prelim algebra because we group in trees with in the way that I said before with fertility. And then we would build our polynomial algebra T plus, which is just indexed now by populated indices. We can forget about the zero part. And that would be just endowing T, the model space, with the so far unnamed Hopf algebra structure that Lorenzo very kindly referred to in his lecture. And the Prelim morphism property then transfers to a Hopf algebra morphism property with respect to Konkheimer. Similar principle holds for other equations. So we computed all of this also in the case of generalized parabolic Anderson model, where you have to treat polynomial decorations, and we expect something like this to be a general principle between multi-indices and the tree-based description in regularity structures. So maybe very quickly just give a final remarks. So we see that multi-indices in the end provide a coarser description than trees, and it has some effects. So we replace the combinatorics of trees by some more Lie geometric arguments, in a sense, while still preserving the inductive type of arguments that Ilya was describing before. So we can still do these inductive constructions. And we expect this to be, this coarser description to be maybe more efficient for some applications in regularity structures, but that's still something that we're thinking about. And more importantly, we still hope that it allows for negative renormalization. So this would be pretty much useless if in the end, to perform negative renormalization, we would have to go back to trees. But we expect that that's not the case, and we have some hints already. On the one hand, we can recover translation of rough paths, as in the paper by Ivan, Ilya, Peter, and Rosa, and that's already done in the paper. And on the other hand, we are now working, so finishing joint work also with Pablo Tsatsoulis in the University of Bielefeld, where we are renormalizing the quasilinear SPDE in the full subcritical regime with some assumptions on the noise, which are spectral gap inequality assumptions. And we're doing it in a BPHC type, so not really BPHC, but kind of resembles something like that. And we can do it without going back to trees, so we can do it at the level of multi-indices. And of course, an open question is how we would build the full algebraic structure of the renormalization group to see that actually this fact that we can do negative renormalization is completely true. Thank you.
Yes. Thank you for a nice talk. So I have two questions. The first one is, if you say your Prelim algebra is not free, have you found like explicit examples of identities that your Prelim algebra satisfy, where the purely algebra would not satisfy?
Yes, so that's a good question. In a certain sense, the Prelim algebra that we define is closer to what you would expect directly from the vector fields, not really from trees. So the kind of identities that you find are the ones given by Leibniz rule or this kind of commutations. At the level of the algebra, of the Prelim algebra with multi-indices, what we see is that, I mean, we can compute, we know what the ideal, I mean, how the ideal we quotient Grossman-Larson is. So it's just we identify two trees, we say they are equivalent if they have the same amount of nodes with the same decorations, modulo the symmetry factors of the trees. So that should be somehow related.
I also a question, maybe like more a remark, don't know, like suggestion, probably. So like you mentioned, like you applied your theory just to study an OD, like to study. So in some sense, you know, this is like also a new two-dimension with at least with Kohn-Kreimer and Bacher. So maybe like maybe does this algebraic formalism could be interesting for numerical analysis because like this is first reason why trees appeared, like and they get so popular, it's numerical analysis. Maybe like some equivalent of B series and with this object, maybe some numerical method, or I don't know.
Yeah, I have no idea if this would be of help in numerical analysis, but that's definitely something that I want to think about. So yeah. Also, there's it's definitely very, very interesting. So of course we can also do like reformulate B series in terms of multi-indices. That's some computation that we did. Don't know if it will be helpful in the end, but it's definitely interesting to think about it. Yeah.
Yes.
So you say replace combinatorics by lead geometric arguments. Can you elaborate a bit on that?
Yeah, I mean, basically we don't have, I mean, since we are forgetting about trees, we don't need to find combinatorial arguments with trees, so we can forget about symmetry factors and so on. And everything is just, so the basic objects are just derivatives, as I said before, in this Lie algebra. So essentially, everything that's related to grafting trees and cutting trees and whatever is gone in our approach, and it's just replaced by multiplication and derivation. So that's more or less what...
way you can use something from that type of category to gain an insight into the combinatorics, into what would be combinatorics if you read it another way?
We haven't thought about that, but I guess it, yeah, maybe it got some insight on, yeah, but...
But also perhaps some technique that would appear in that setting that would not all be obvious in the other setting. Or do you have something in mind, or do you think this is possible?
Not really, no, in that direction. I think so, but yeah, I mean, but I don't know. I mean, I would have to maybe do some computations to see what kind of things you could expect, but I mean, it has, yeah, potentially it could, but I cannot say that it will.
I have a question about quasilinearity. So in this regulated structure business, there's this one work, I think, by Martin and by Mate, and basically they show that all the machinery works, except that at one step there's this miracle about, I think, a non-local operator appearing, and then in the end it all somehow comes together and it works out. So can you give an explanation in your framework as to what the machinery behind that is?
In our framework, so yes, and the equivalent problem is the following. So if you, okay, let me go to the first slide actually. So the Z0 component is like a placeholder of the nonlinearity itself, so a placeholder for A somehow. So if you then go to the homogeneity, for instance, this square bracket here will not see the beta 0 component because it's multiplied by k, so 0 times whatever. That in the end translates to the fact that for a given homogeneity, you don't have finitely many multi-indices, but you have infinitely many. Like you have, let's say you forget about the E0 component, you have them finitely many, but then for each of them, you have a whole infinite family indexed by this E0 component. In the end, that's not a problem because that somehow can be fed into the induction, but it complicates things because you have to be very careful with these finiteness properties that I mentioned. So if we had really this triangularity in the sense that for a given value of the homogeneity, there are only finitely many multi-indices below it, I think most of the things that we do might simplify a little bit. But since we don't have that, we actually need to have stronger, stronger finiteness properties. But in the end, it's not a problem. So it's, yeah, in the end, I guess it's related to the fact that in the work by Hira, you can do it by transforming the equation also.
Understand correctly that you're saying that you have the equivalent problem, but you can also solve it. But is the mechanism more transparent in your approach?
I mean, from the very beginning, it's so we don't need any non-local stuff. So one advantage is that the way that we are renormalizing things is automatically local, which is, I guess, the main problem in that work. That in the end, the counterterms might not be local, but in the end, they are. For us, the counterterms are always local from the beginning. So